So if the pulse of chemistry is synthesis, then I can keep this title only if giving credit to the talk before. If the pulse of chemistry is synthesis, then the brain of chemistry is analytics. So there's no question about that. You would not understand anything without analytics. So saying this. Well, I decided to walk you through today, not through a specific topic or something into a great detail. I rather would like to give an overview about the architecture of the chair of inorganic and metal organic chemistry, and especially giving credit to the junior researchers which are involved into that. And this is partly an answer, Terence, to the question you said about the support of junior researchers, which I do in my environment. So let's see. This is a very busy, very overcrowded and busy slide, but the message I would like to transmit with that is the following. So there are a couple of people, you see the faces, and we will see a lot of more faces with the students later, and they all represent certain expertises and certain independence and certain collaborative actions within the chair of inorganic and metal organic chemistry. As you mentioned, we do organometallic cluster libraries, we do catalyst synthesis and design, we develop materials for within the context of energy storage, energy conversion. We have activities in photoactive materials, photocatalysts, and we work on hybrid materials in various ways, including adsorption, including flexible behavior, and so on. And there are docents in the team or associated to the team, which is people who have already completed their habilitations. There are 2 junior fellows who run their own independent research groups. There are habilitants sitting on positions which are allocated to the chair. There are advanced postdocs coming by various sources of funding, like the Humboldt Foundation. And of course, there's academic staff. So all of them are associated to the chair in various formats. If you look to these few icons here around, you may recognize certain connected areas. So this here, this circles around clusters and nanoparticles. This here starts with the MOF materials, then it penetrates through the energy-related stuff. Then we have MOF-derived materials, the photophysical properties we have, and here we have a project which relates to clean water, and there is above something which is connected to gas sorption, selective gas sorption, and separation technologies based on porous materials. So there's a certain logic about the interrelation of the various topics, and you see here in this inner circle, of course, clusters, but also nanoparticles I mentioned. Then supramolecular architectures and porous materials are related to each other, and it's all circling around our capacity in synthesis, obviously, which is deeply rooted in organometallic coordination chemistry. And this is how I was brought up here as a student of Wolfgang Herrmann in the tradition of the chair I'm now representing, going down all the way to Walter Hieber and people like this. So first of all, I would like to remind you to Julian Warnen. I think he already gave a talk in this series. So he joined us not long ago, and he is just building up his own group on functional molecules and materials for energy conversion. His competence is from organic chemistry mainly, but then he moved into the design of artificial photosynthesis systems by molecular engineering, and he is building up his group on organic photoredox transformations beyond the classical solar fuel applications, and we come back to this in a minute. So Julian is sharing supervision of students, and I show you this. So the orange or yellow marked ones are students where Julian is in lead. So that would be his independent projects or the projects which he is leading, and I will give an example or a close mentioning on this in a minute. And the blue ones, and this will be the color code throughout the talk. This is projects which are students which are basically on my funds or which are directly reporting to me as well. However, they would do work which is not in the absolute center of Julian's expertise. So, for example, electrosensors or some electrocatalysts. When it comes down to photocatalyst materials, and of course there is a strong link. So, some examples, and I will zoom into one specific one in a minute. So, for example, what do we do? What do we understand about the electrocatalysis? So mainly we work on MOF derivatives. MOF derivatives are systems which transform during the operation. So, and this has to do with the oxygen evolution reaction. And this is a joint PhD supervision as well with Alexander Bandarenka from the physics department. And this one is Sujin Hu, which is a joint student. Here on that side, this is the development of the supramolecular photocatalyst systems where Julian is very much involved. And that's a very nice project together with Angela Cassini, mainly with Bernd Rieger, but we also integrate Natalia Shustova via the TUM Institute of Advanced Studies. She is a professor on photophysics and photophysical materials and MOF-related materials at the South Carolina University. That is basically integration of photosensitizers and catalysts in the metal organic framework, which operates as a host for these systems for CO2 reduction to CO. Two more examples on this e-conversion subgroup, as it's called in our chair, are electrosensors. I have mentioned that. This is Chen-Yu Chu. Basically his work in his thesis. He is writing up this, and I'm particularly proud of that project because we have started collaboration with Martin Elsner recently. It's already went into a publication, and this has to do with the detection of pollutants in water by a MOF-based voltammetric sensor. I will zoom in this project in a second. Just mentioning another example, which we call clusters in cages. This is Katrin Kollmannsberger, and also Julian is involved in this. And here we integrate atom-precise clusters made by wet chemistry into the cages of a MOF to keep them, so to say, safe from aggregation and growth by the confinement, and to allow for the catalytic or the investigation of their catalytic properties in such a hybrid system. But now let's zoom into this project for a moment. So what Chen-Yu did is the following. We took from the literature a recipe of a known so-called PCN, metal organic framework, which is a porphyrin type system, which has this kind of hexagonal channel structure. You can synthesize a whole series of related MOF materials of that kind. They are very hydrophobic, and they do us a favor to nicely spread on the liquid air water interface. And this gives you the opportunity to transfer them to a substrate. It can be ITO, it can be different things. And you see here this nice worm-like, rod-like MOF crystallites on the scale of a couple of microns. They are nicely attached to the conductive oxide glass. And this basically gives you the electrode for the voltammetric sensor. So if, for example, nitrobenzene would be the analyte, we would see the this characteristic redox potential, or the current when the potential is correct for the oxidation of the or the oxidation or reduction, depends on what you do, of the nitrobenzene to, in this case, the phenyl hydroxylamine. And this gives you in the cyclovoltammetry this kind of red big trace here, yeah, and that would be the manganese PCN 222 ITO electrode, and the other traces refer to the blank ITO, the porphyrin without the manganese, then the manganese the manganese methylated porphyrin, but you see between the methylated porphyrin and the integrated one into the MOF a big difference, and this has of course to do with the kind of porosity of the material and the accumulation of the analytes close to the reaction centers. So this is the kind of work we do, combining thin film work, MOF work, and electrosensors application. Now I introduce a second subgroup in my team. This is Dominik Halter. He also just recently joined. I think you have seen this slide before when he was introducing himself again in this inorganic chemistry talks, and he is going to set up this kind of energy-related electrocatalysis work. And I emphasize the link between his activity and his expertise and ours. Obviously, he has a strong background in molecular catalyst design in organometallic chemistry. He has been with Jeff Long at the Berkeley, learned much about MOFs, and he's going to integrate both aspects in his research. And this is then obviously kind of the cross-sectional situation between the two of us. Again, the same structure. He just started building up his own team within his independent area of targets. But there is, of course, a link to us based on the application of MOFs in various contexts. And he also shares supervision of students together with Julian and others in my group. I mentioned here a couple of aspects. So, for example, MOFs as nanoreactors in the context of catalysis. There's, of course, links to Karina's work in my group. There's also a link to the electrosensing work I just mentioned. Let's move to another very important subgroup, which is, we call it the supramolecular catalysis subgroup, if you like. And this is connected with Mirza Tsukoya and his expertise in catalysis, molecular catalysis, but also this more supra-organized catalysis systems, which is, he calls himself the micellar catalysis team. And there are a couple of aspects of interest which link his work to ours. So the common motive is that you have nanoparticles or micelles, so nano objects, which are important for doing the job. So in our case, we put the surfactant stabilized metal nanoparticles inside the MOF material, or we just work with the nanoparticles in colloidal solution themselves. So confinement and active site modulation plays a role. Of course, then the aggregate size plays a role, and host-guest contacts and multiphase reactions plays a role. Here we have kind of the solid-liquid interface. Here you have more or less this kind of colloidal, soft colloidal micellar liquid interface. And the reactions which we are looking at are various forms of cascade reactions in the MOF system, epoxidation, cyclopropionation, CO2 activation, alkyne semihydrogenations, and more, which can be implemented in both worlds, if I may say it like this. So specifically, I will highlight now this central topic in a minute, but it's nicely put in between these two other PhD projects. So, for example, Lena Steiger is working on palladium nanocolloids for the alkyne semihydrogenation, and there's a link between her and Jean Fan, where the nanoparticles are integrated into the MOF framework. And it goes down now to Karina, and she is doing much more sophisticated MOF design for diastereoselective, for example, epoxidations or related reactions. And there's a nice collaboration now going on with Matthias Senji from the Trinity College in Dublin. He is also a TUM IIS member. She is working also on porphyrin MOFs, and the Senji group is kind of the world-leading people on non-classical porphyrins, kind of concave porphyrins, and she's now integrating them into her MOFs, and we will investigate it for this specific catalytic properties. But let's zoom into Jean Phan's thesis, and I can show you here kind of the effects you can integrate into these heterogeneous hybrid systems by defect engineering of MOF materials. So what Jean was doing, she developed a ultra-fast 1 minute, very smooth or very kind of ambient condition synthesis of the whole MOF. So by a clever choice of precursors. Why is this important? It's important because if you have long reaction times or high temperature, which is usually the case in MOF synthesis, then you would aggregate your nanoparticles. So if you want to keep preformed palladium nanoparticles stable in terms of size distribution, then you need to have this kind of ultra-fast, smooth synthesis conditions. Then more, she integrated a special kind of defect generating linker by a mixed linker approach into the MOF network. So we have this kind of isophthalic acid linker with this long chain here. And these long chains point into the cavities. So what you do, you change the hydrophilicity of the MOF material of the host, and this has a drastic effect on the catalytic performance. So the red trace here is just the unmodified, not defect engineered MOF host material, which has a very poor catalytic performance. And if you increase the chain length of your defect linker, then you increase the wetting you increase the hydrophobicity of your host matrix, and this boosts the catalytic activity very much. So in 2 hours to 100%. So this is one example of fine-tuning some catalyst system, which is nanoparticle based by integration into a defect engineered tailored MOF system. So the photomaterials subgroup, this is the domain of Alexander Pötig. You know him very well. He is known for his supramolecular organometallics and for his pillarplex chemistry. He already completed his habilitation, so he is a Privatdozent, and this is his growing team. And of course, he is a coordination chemist, an organometallic chemist, a structural chemist, and he is, of course, an academic staff of the Catalysis Research Center. However, he basically voluntarily associated kind of intellectually his group to us, and he takes also much part in the co-supervision of a couple of ongoing projects. What brings us together is our engagement in the DFG priority program 1928, where he has his own independent project, but his background in photophysical or photophysics of coordination compounds is important for the topic of photoelectroactive coordination networks, which is done in my group with these people here, also in part related to this priority program. For example, Sebastian Weishäupl and Simon Deger, they are developing special chromophores for integration to MOFs, and this is why Alexander Pötig is integrated and leading this kind of supramolecular photomaterials subgroup here. A couple of projects, just to give you a taste what we are doing. So photoactive MOFs means that we integrate chromophores into the MOF as a linker. So these are this carbazole chemistry, and Sebastian Weishäupl is doing this and we aim for kind of multi-photon absorption properties. And this is done in collaboration with Jürgen Hauer. Joao, for example, is integrating redox activity into the MOFs by, in this case, taking this anthraquinone type of linkers, which are then packed together in a coordination network. And I will zoom into this project in a second. And I have to give a lot of credit to Margit. She has went through a long frustration period, but kept on working to come up with this all sulfur analog to the 1,3,5 tricarboxylic acid of benzene. And this is basically the all sulfur analogous linker of a famous BTC linker, which is integrated into many MOFs. So we aim here to enhance the electric conductivity properties of MOFs when we are able to integrate this into the whole system. But she is still working on this problem. Now let's have a look at Joao's redox active MOF system in more detail. So what you see here in all of these kind of images, that this is classic crystal chemistry, crystal engineering, and his thesis is heavily rooted in crystallography and crystal growing, basically. So what he has been able to show is that by packing this anthraquinone linkers densely into the whole network, and it depends, the packing type depends on the metal you choose. It's very similar but distinctly different. So zinc and cadmium would make slightly different packing motifs, but in the zinc case, we were able to show that the reduced version of the quinone system, this would be the hydroquinone, can be stabilized by hydrogen bridging as a consequence of the packing density. And this is important because here you can then switch between the two states. So the reduced and the oxidized stage of the on the anthraquinone, in a way, you can integrate the anthraquinone or the process of the direct conversion of oxygen and hydrogen to hydrogen peroxide into a metal organic framework. So he has been able to show that you can switch between this oxidized and reduced status of the framework depending on the conditions of the system, and he was able to detect the formation of the hydrogen peroxide. Unfortunately, this process is not yet catalytic, but that would be an obvious goal what we want to achieve. So molecular oxygen activation by redox switchable anthraquinone-based metal organic frameworks was the title of his inorganic chemistry paper. Now let's say a few words of the hybrid materials subgroup, which is headed by Gregor Kieslich, who is a Thumann Junior Fellow like Dominik Halter. He is also running his own group, which is on crystal chemistry of functional materials, and his strong point are molecular perovskites. So we have been publishing lots of papers together. So these orange-brown ones are examples of his publication output without my name on the paper, to make that clear. So an independent work related to his own career. And this would be joint supervised, the outcome of jointly supervised projects with students which are shared between the two of us. And I will give a quick update on some specific project in a second on what Jan Berger is doing. This is shown here. So this is integrated in the research unit 2433. It's called MOF switches. And here we integrate gas sorption selectivity into certain metal organic frameworks. This is again such an hexagonal system, which is, this is not good to read, which is essentially a rigid one, but the flexible property comes from the dangling side groups. These are side groups of different length and chemistry. So this would be saturated or unsaturated side groups of different length. And we could show that if you put in these ones or these ones, they have specific, they enhance the selectivity of the gas sorption of the system. So for example, if you want to separate two rather similar linear molecules of the same basic dimension, just by different by their quadrupolar moments and some weak interaction forces, then we could show that the certain choice of these side groups make a big difference, and that would be kind of a kinetic separation effect. And these are the breakthrough curves on certain columns, which we have been analyzing. So cutting a long, complicated story short, by kind of the engineering of the internal surface of a metal organic framework in the correct way, you can modulate the kinetics of the sorption, the penetration of the molecules into the framework, finding their adsorption places. And this gives you another dimension of tailoring the gas sorption selectivity of this kind of sorbents. So we call this designing adsorptive gating. This brings me to another dimension of sorption, and this is a new junior research group leader. It is Shoma Mukherjee, who is currently a fellow of the Alexander von Humboldt Foundation, but he will continue as a Marie Curie fellow of the European Union, and he has been building up his own work road related to liquid sorption problems. So for example, water decontamination from so-called forever chemicals. So these are a certain fluorinated tensides, if you like, and they have been banned by the European Union. So the threshold of their concentration in drinking water has been newly set, and there is an increasing problem to basically purify groundwater, contaminated groundwater and drinking water from these pollutants. And obviously, this is a project which relates very much to the expertise of Jürgen Dreves from the Chair of Urban Water Systems Engineering at TUM. So my role basically, and Terence, this is an answer giving to the question you have mentioned before. My role is just to support Shoma. So I won't touch these kind of things. So he will be developing this as much independent as possible. And he already were able to recruit a student, and the whole thing is now growing. I give you a kind of a short update about the concept on the next transparency. So this is kind of the roadmap of steps which have been you have to take into account. So we do a proof of concept, then this needs to be expanded, and there must be practical implementations, and we are just at the first column. And what is done, we investigate, of course, metal organic frameworks, play with the surface hydrophobicity, with the hierarchical porosity, and of course it must be mechanical and chemically stable. But there are, of course, problems with multiple step synthesis and compromised porosity if you integrate various components in a working hybrid material. You have to work against the established activated carbon, which is cheap and simple. So granulated activated carbon is the adsorbent of choice for this kind of water purification. However, there are limits, and the granulated activated carbon is less selective in the capturing of these specific pollutants. And one of the ideas to play with the, as I have introduced it before, with the internal surface area of these high surface area metal organic frameworks by fluorinated ligands or by other ways to play with the hydrophilicity and hydrophobicity. And hot off the laboratory is shown kind of this slide to give you at least a taste. We cannot disclose too much about the nature of MOF1 for reasons which are probably obvious. So if you look at this first entry here, this is the granulated activated carbon, which is the color code green, yellow, and red. These are three different fluorinated pollutants which need to be removed. And if you look at, for example, 1H or this 1F4OS, then you see that this one and this one clearly beats the granulated activated carbon. There's, of course, a variation of the selectivities and the retention or removal efficiencies depending on the MOF type and depending whether we modified it or not. And we even have been able, or Schoma has been able to even come up with better performances as shown here. So this is an update of the MOF-SORB team, and I'm super happy about the development of the project. We are at the level of 100 microgram per liter, but also we can go down to 10 micrograms per liter, and there will be more updates coming maybe soon. And this is just a call to the organizers of the of the TUM talks of the inorganic chemistry. Just invite Schoma and give him the floor to introduce himself to you. I move on. Now I'm at the point where I have to give the answer to the question why I kept from the very beginning of my independent research activities the topic of cluster chemistry, or let's say mixed metal coordination chemistry. Over 20 years now, most of the time since 2000 or so, I think Christian Gemel joined the group as a postdoc in 2001, I think, and we just found out that we are now together 20 years. And I have to give a big thank you to him, because he was the one who, with me, basically persistently followed this route. Look at that, we published together 100 papers so far in these 20 years, about 2,000 citations, and an H index of about 30 of that particular organometallics cluster work. But look at the comparison to the MOF-related work in the same time span of 20 years. I published 400 papers, and this earned us 10 times the citations, or 20,000 citations. So this gives you a relationship of the recognition of the scientific community from the bibliometric point of view. Right now, there are a couple of engaged students who do this or follow this kind of footsteps of the other ones who were with me in the almost 30 years we are doing this now. And in the last, let's say, 5, 6, 7 years, we were able to find examples that these cluster systems show interesting surface reactivity. Such examples have been very complicated to obtain, kind of single shot lucky cases, but it told us that it's possible. And then we moved into larger and larger aggregates. So this Angewandte image in 2018, we have been very proud of. This was the largest cluster we could make. It's about 55 atoms, aluminum and copper. And I'm pretty happy about the outcome of that, because at the early times when Christian joined, we wrote a DFG proposal, basically exactly proposing something like that we should be able to make these systems all hydrocarbon protected based on group 13 chemistry, low valent group 13 chemistry, and these aluminum organometallics, they should somehow act as surfactants to stabilize a metal-rich kernel. We wrote the proposal, and the referees didn't like it. I quote from their referee report, that sounds fascinating, but this will never work. Well, they were right. It took us almost 20 years, but it did work. And we are now at the point to transform or to translate our kind of classical knowledge of organometallic synthesis of these cluster systems into something more high throughput, more systematic. And so we just implemented in the glove box, because all this chemistry is air sensitive. It hates water. It would be destroyed by oxygen. So we do all this in the glove box, and this is a pipetting robot. So now we do previously the Schlenk chemistry in a parallel fashion into the glove box. And this is what Ivan Ansiburov has just set up. Okay. So thanks to the Deutsche Forschungsgemeinschaft, this kind of esoteric cluster chemistry has found now some recognition. We were able to defend and get funded a Reinhard Koselleck project entitled Living Libraries of Intermetallic Superatoms. And the answer to Terrence's question is, what is so fascinating about that? I think what fascinates me now is the opportunity to develop a completely new approach into organometallic chemistry, an approach which is well known in pharmaceutical chemistry. It's well known in the medicinal chemistry, that you work with libraries and you work with large ensembles of related molecules. However, this is typically limited to peptides, nucleic bases, DNA, etc., where it's well behaved in terms of pH, water, oxygen, ambient conditions, and so on. However, if you work with organometallics, then you have to avoid water. You have to avoid oxygen, and you are working with thermally extremely labile systems. So how to implement the concept of libraries and working with huge mixtures, dynamic mixtures, into the world of organometallic cluster chemistry? And I think this is a fascinating idea to do so. Nobody has done this before, and you need to know, you need to have a certain knowledge about the base chemistry, and I think we have this knowledge at this point. And this was basically the idea of this Koselleck project. So what we do, we generate cluster libraries by organometallic chemistry, and then we have to develop a methodology based on spectroscopy and mixing with crystallography and theory to basically come up with an analysis of this whole library. So it's heavily based on mass spectrometry, but adapted to the organometallic species we are working with. And the far goal is that we come up with small molecule or small cluster models which do chemistry related to heterogeneous catalysts, specific heterogeneous catalysts that would be intermetallic ones, which is a hot topic in heterogeneous catalysis. So in a way, we are searching our libraries for interesting species in a kind of a high throughput or very efficient way to decide which one is worth to be looked at, which would be an interesting model of such transformations like CO2 reduction or hydrogenation or oxidation catalysis. So what we do, we have a pool of all combinations we see in the mass spectrum. We have to find a way to make an exact composition assignment. This is done by isotope labeling and by analogous labeling. And we have to decide in our data retrieved from the mass spectrometer, is it a molecular ion? So that would mean, is it really the one species which is in solution as well, or is it a fragment of such a species. This can be done by various techniques. At the moment, we are using kind of the variation of the collision energy, make a statistical evaluation, and then we come up with a list of molecular ions. I can show you on this specific example what labeling means. So we are organometallic chemists. So that means if we want to work with a compound which is metal labeled, we have to go for a specific isotopically enriched zinc, for example. So we made this 68 zinc Cp star compound, and if you have that, then it has a characteristic, it creates a characteristic shift in our mass spectra, because everywhere where this zinc shows up, which is 68, you have an enrichment of a specific amount of units. This means 3 times the zinc is integrated in this peak if you see this 8, this delta of 8 from this to this. But this helps us not alone. We need to label the ligand as well. That would be the all-methyl substituted Cp star, and that would be the tetramethyl monoethyl substituted Cp star. So this would give a shift of 14. And then you can also come up with how many Cp star ligands are in this kind of multiplet. And by doing this in multiple times, you can extract from your data that, for example, that safely this species with hydrosolution would be the copper 7 zinc 3 Cp star 3 mesotyl 4. And by combining this kind of labeling, we can basically work ourselves through all the dozens and dozens of peak envelopes which you create in such an experiment. And Max Schütz in his thesis is the hero of that. So he developed more or less the methodology from which now we can retrieve this kind of lists. This is just a shortcut of the whole. So there are hundreds of species which we are harvesting. Some of them, the red ones, we could isolate and classically characterized by single crystal techniques combined with theoretical modeling. Some are still elusive. And as I said before, there are species which you cannot isolate, but these are the interesting ones. The ones you can isolate are typically less reactive. The ones you cannot so easily isolate probably do an interesting job. So the green ones, these ones, where we are sure that the sum formula is correct because of the reasons I mentioned before, they show reactivity against hydrogen and CO2, and eventually we can even see the formation of formic acid in such cluster libraries. So this gives you a taste of the dimension, the development of this kind of chemistry in the future. So as I close my walking through all these junior groups and associated groups of the chair of inorganic and metal organic chemistry by mentioning Markus Drees. He is running his own kind of business in the area of computational organometallics. And you see on this slide a couple of examples where he contributed his expertise to certain projects. You see, for example, one with Kieslich, and you see others with Mirza. So we are very happy that Markus is still active as a researcher and is not completely lost in his responsibilities as the kind of the managing workforce of the faculty graduate school. So thank you, Markus, for your continuous support of these teams here. Ladies and gentlemen, I think it took me too long and it was too dense and too much. So I close my presentation at this point, giving you a little bit of a perspective what's coming next, and then I am done in a few seconds. So right now we are very happy that together with Angela Cassini, we were integrated in the TUM Innovation Network Artemis, and this deals with metal organic framework and metal organic cage related supramolecular entities for electrocatalysis, but also for kind of regenerative medicine. And we are looking forward to develop this probably into a larger enterprise with our colleagues from the physics department, the informatics, the electrical engineering, and the mechanical engineering. As some of you also know, that we are anxiously waiting for the decision of a proposal submitted to the DFG on establishing ein Graduiertenkolleg, a research training group. We are expecting the decision by November soon. It also is related to these kind of classes of materials. We are absolutely convinced that we wrote a fantastic proposal. We don't know what the referees think about it. We will see what the decision brings to us. And yeah, I like to share with you a personal challenge. So we already have this kind of cluster kind of chemistry running for so many years now with the Reinhard Koselleck project now. And probably we will be able, if we are lucky, I mentioned that you need luck, that our synthesis and new method concept in organometallic cluster library chemistry will work out. And if this does, I think I have a unique chance to submit a strong proposal to the ERC for integration of high throughput experiment and theory, machine learning and chemical robotics to organometallics. Thank you, ladies and gentlemen, for your patience. I close my talk. Sorry, I have to go back. Say again, thank you to the junior people in my group. And I have to give a big applause to the students who have done all the work over so many years. I have been talking to you and presenting to you. Thank you for your attention.